Did you see what happened over there?
Oh no, you have to inform me when you get there.
That's the car over there. What happened? The car was driving at the suggested speed limit, but once he got to the turn, the car tumbled over. Let's look at the map to see what's wrong with the highway.
Looks like there's a flaw in the road.
Do you think it has something to do with curvature? The highway seems too curved for a road.
Potentially. If the road is too curved, then cars traveling at the speed limit will not be able to make sudden turns. That's why most roads and highways are only slightly curved.
True, roads can be modeled by graphs. At each point on the graph, a circle tangent to the curve can be drawn that maps the curvature of the road. When the road is really curved, a small circle can be drawn with a small radius, but the curvature is really large. When the road is only slightly curved, a large circle can be drawn with a large radius with a small curvature.
I wonder if there's a formula for the radius of curvature.
Let's ask our math major, Bruce.
The radius of curvature r is simply the reciprocal of the curvature k. So we know that r is equal to 1 over k. Let's do a graph here. Here is a curvature. Let's do two lines. And we have 2 points, which is P1 and P2. And we also have delta S. And we have delta theta. And we know that delta S is the length of the arc P1. And delta theta is the angle turned by the tangent line as it moves from P to P1. So the curvature of the arc from P to P1 is given by delta S over delta theta over delta S. So the curvature K at point P is given by K is equal to limit as delta theta approaches 0, delta theta over delta S, which is equal to d theta over ds. So to find d theta over dx, we need the chain rule, which is equal to d theta over dx times dx over ds. We know that tangent theta is equal to dy to dx. So theta is equal to arctangent of dy to dx. Now we know that d theta to dx is equal to d to dx of arctangent dy to dx. And now let's differentiate this. So d to dx of arctangent dy to dx is equal to the quantity of d to dx of dy to dx all over 1 plus dy to dx squared, which is equal to the second derivative of dy dx over 1 plus dy dx squared. We also need dx to ds, which is given by dx over ds is equal to 1 over dx to dx, which is equal to 1 over the square root of 1 plus dy dx squared. Now let's integrate all these together to get the formula of the curvature k. K is equal to d theta to ds is equal to a second derivative of dy dx over the quantity of 1 plus dy over dx squared to the 3/2. And the radius of the curvature is just the reciprocal of the above expression, which is r is equal to 1, the quantity of 1 plus dy over dx squared to the 3/2 over second derivative dy dx. And since the radius needs to be positive, So we take the absolute value of the denominator of the fraction, and we get the formula of the radius of curvature.
Alright, I think I understand what radius of curvature is, but I still don't know how it will help us fix the problem.
Lucky for us, Supov is on the scene. Maybe he knows the answer.
Alright then. I'm actually already at the Sierra Padre with my cameraman. The American Association of State Highway Transportation Officials establishes guidelines on roadway design, one of them being the minimum radius of curvature of a curve on a road. So this curve on Sierra Padre is particularly interesting because there have been 2 accidents where a car was speeding and collided with something on the side of the road. So I actually calculated the radius of curvature along multiple points along this road using some simple GIS software and a compass. So a visual representation of what I did is that I put the latitudinal data on this, the x-axis, and converted it into actual distance. And I took my compass data and used that to convert it into the first derivative slopes, the tangent lines of the curve, by using the fact that tangent theta is equal to the first derivative. And for the second derivative of the formula, I was able to approximate that using the first derivative of adjacent points and taking the average of them. So the actual guideline is given by this formula, where V is the speed of the car, E max is the maximum roadway super elevation, which is basically the gradient of the cross section of the road, and F max is the maximum side friction coefficient, which is the coefficient of friction between the tire and the asphalt. So using all of that, I got out of all the radii of curvature I calculated, the minimum was 240.83 feet. So the speed limit along this road is 35 miles per hour, but I think you know by now that nobody actually goes at that speed. So I calculated the minimum radii of curvature for different speeds. So at 40 miles per hour, we would get a minimum radius of curvature of 147.7 feet, but at 50 miles an hour, we would have a minimum radius of curvature of 230.78 feet, which is already pushing on the value of 240.83 feet. So the road itself isn't designed dangerous, but the fact that cars are going too fast is putting them in danger. And especially when you're on the downward slope here, it's really easy to push past the speed limit and potentially endanger yourself.
Okay, I understand now. The city has to decrease the curvature by increasing R, and since the curvature K is equal to 1 over R, increasing radius will decrease the curvature.
Yes, I agree with you. The city should restructure the road so that the highway is not as curved and not as dangerous for people to drive on. That way, future cars won't experience crashes like this anymore.